I'm Nico. Today we're going to be talking about machine learning models and the way that you measure them, specifically the performance metrics that you're using to measure the performance of your machine learning algorithms that you're using in hopefully production or every day. So for some people, performance metrics and the term performance metrics might be completely unknown, which is completely fine. Not everyone knows what it is if you're completely new to data science, or maybe you know what a performance metric is, but you're not quite familiar with that there being different ones. So usually when we're talking about performance for a machine learning model, everyone or most people are thinking of accuracy, because accuracy is probably the most known and the most used performance metric for models. And it can be really good depending on the problem that you have. So accuracy is fine as long as you're taking into account the problem you have. So it does tell you how well your model is performing, but it's not quite the full story. And with that, I mean that if you have an example with a very skewed data set, then a high accuracy might not show you what's actually going on under the hood. What I mean by that is that, given an example, we're going to be making an example today with a binary output because it just makes it easier for me to explain, where 1 is the positive and 0 is the negative. Given that, then if you're using accuracy as your measure, but you have 95 of class A and 5 of class B out of the 100 samples, then if you just predict everyone in the dataset to have class A as the label, then you will have an accuracy that says 95. So you predicted 100 to class A. Now you have an accuracy of 95 because you predicted the 95 correct, but you don't actually know that you predicted the 5 wrong. And if you're using a model like this in production, that could actually lead to either really destructive results or a skewed image of what's actually going on under the hood. Because most machine learning models, you can't really see the logic that goes on. For decision trees, you can, but for other advanced machine learning models, especially neural networks and like deep learning, you have no idea what's going on behind the scenes under the hood. So that's why you want to measure it with the right metrics. Usually when a model makes predictions, that prediction falls into one of 4 categories. So we have true positives, we have true negatives, we have false positives, and we have false negatives. Now, again, as I mentioned, we're using a binary example just to make everything easier. The example that I'm going to be using is cancer patients because it's very relatable for a lot of people, and we all know what's what in that case. So in our example, 95 of the patients don't have cancer, and 5 of the patients has cancer. So now we know that we have a quite unbalanced data set, and we kind of want to get an insight into how to do this. So looking at the true positives and the false positives and the true negatives and the false negatives, a true positive is when the model predicts that a patient has cancer and it actually also has cancer. A true negative is when the model predicts that a patient doesn't have cancer and that patient also does not have cancer. And a false positive is when the model predicts having cancer, but the patient is cancer free. And a false negative is when the model predicts the patient as being cancer free, but the patient actually has cancer. So that's the most disastrous example in our case, but this is very problem based, and it depends on the domain that you're using the machine learning in. So this doesn't apply the same to all problems. If we take a look at the accuracy for the example that we've just made, now we would have an accuracy of 95%, which would initially be very, very good if we had a balanced data set, because if we wanted to get an accuracy of 95% on a balanced data set, then we would have a model that needs to predict well on both classes. But since we, in our problem, don't have a balanced data set, now accuracy is not really giving you insight into what's going on behind the scenes, and you actually might be led to believe that it's performing well. And the reason why I'm using this data set as well is because I find that, in my experience at least, that balanced data sets don't really exist too much in the real world. They're always imbalanced, so having metrics that actually can look into this will give you a better insight as to what's going on. If we want to take a look at the metrics that can look into these kind of unbalanced data sets, we would need to look into precision, recall, and F1 score. The precision is a measure of how trustable your model is when it makes its prediction. So taking our example, if it predicts a patient doesn't have cancer, how trustable is it? Or if it predicts how a patient has cancer, how trustable is it in that case? If you're looking at recall, then that is when the model makes the predictions out of the total of that class, how good is it at predicting that class? So if we just take our non-cancer patients, how many of the 5 cancer patients does it predict So how many of the class? So if we only predicted 2 of the cancer patients and they actually did have cancer, we would have a high precision because all predicted cancer patients had cancer, but our recall would be low because we only predicted 2 out of 5. So hopefully that kind of gives you an understanding of the difference between the two measurements. They are correlated, but usually if you increase one, the other decreases. So I know they sound kind of similar, but hopefully the examples I'm about to give will kind of give you a better insight as to how they work. F1 score, on the other hand, is kind of a harmonic mean between recall and precision. So it's a really good measure that you can use if you just want to get an overall combined score for your F1 and recall. So if you have high accuracy and a high F1 score, then you know that all your metrics and your model in general is performing very well on most classes, and just in general its predictions. Now, if you want to know what classes is doing less well on, then you'd have to look at the individual class metrics, because these metrics are also being done on a class-by-class basis. Giving some examples, we can start with a case in which we have a high precision and a high recall. In this case, we have a model that is very trustable when it makes its predictions, and it also categorizes all of the examples correct. So this is a model that is correct all of the time, 100% of the time. So that would be very, very good. I don't think I've actually ever seen a model that has done that in production. So if you have seen one, I would love to hear about it. Take in mind, this is a model that is in production. So that is working with real world data and not some made up data set or in a experimental setup scenario. Another case is then when you have high recall, you have low precision. Now this means that our model, in the example that we gave before, we've predicted 100 patients being cancer-free. We will have high recall, at least for the class of non-cancer patients, because we predicted all the cancer patients, but the precision would be low because we have included other classes than the class we wanted to predict. So it's not very trustable when it makes its prediction. So it predicted all of them, but the precision is low because it's not very trustable. We are including some of the other class into our classification. Then we have the scenario of we're having low recall, but we have high precision. That means that out of the total amount of samples of a class, we didn't predict that many, but when we did, we were correct. So if we take an example of predicting 2 of the 5 cancer patients having cancer, now we've predicted them correct. They do have cancer and we predicted that. So the precision would be high, but we've only predicted 2 out of 5. So the recall would be low because we've got less than half classified as the class it should be classified as. Then there's the last case where you have low recall and low precision, and in that case it's not really good at all. So I think that would be also something to look into, like in the data itself, what's going on wrong under the hood. I think the best way to actually try and explain and visualize this problem is to go into a notebook and show you a live example of what's going on, and then we can kind of see the measures in practice. Okay, so now I've just entered the notebook that we're going to try and visualize the example, actually put them into practice so we can see kind of how it looks in practice. For this, I'm just going to be importing NumPy, Pandas, and then a package from sklearn, which is the classification metrics that will give us all the performance metrics that we've been talking about now. So we can kind of see how it works. So the first thing I'm doing is I'm creating the cancer patient data set. In this, I am basically saying that I want to create an array of 95 zeros, and then I'll append 5 ones to the 95 zeros. So now I have a data set of 100 data points where I have 95 cancer-free patients and 5 cancer patients. And I've just named the column target to be able to print these values. So just for verification purposes, you can see that there is 95 cancer-free patients and 5 cancer patients. Also, just as a sanity check, we do see that if we check the tail here, the reason I'm using 7 here is to see more than the last 5, because the last 5 we know are ones, so I just wanted to make sure. So basically we see here that we do have zeros leading up to the last 5 entries, which are then ones, which means they are cancer patients. So if we then take the example that we had before, mentioned that all the patients that we have, we predict to be cancer-free. That means that what we're predicting is all the patients will have a 0 in our binary example. So I'm basically just using NumPy to create an array consisting only of zeros, and then I'm using classification report where the first entry would be your true variables and the second entry would be your predicted variables. So running this, we see that we have some different metrics in this print statement, and we'll just quickly go through what it is. So if we start with support basically means how many of that sample is in the original dataset or in the true label dataset. So for our 0 variable, we do see that we have 95 entries, which is correct. And we have 5 entries for the ones. So that's the cancer patients, which is also correct. So if we take a look at the precision, we do see that we have some different numbers depending on the class. We have a macro average and a weighted average. So usually what I would use when I'm using my model is I would first take a look at the macro average, and then if I needed to know some more class specific numbers, then I would look at the individual metrics for that class. So our precision is 95.95 because again, this is only because we sum to 100, so it's going to be like one data point is equal to 0.01 points in these scorings. So imagine this as like a percent of the whole, rather than one being a patient, just for clarification purposes. But we do see that we have a precision of 95 because we got 95 out of the 100 as the patients, but it is not 100 because we have also included classes that do not belong to the 0 class, so the cancer-free class, so our precision won't be full or max. Our recall, however, is 1 because we have recognized every single cancer-free patient, therefore the recall will be 1 as there's none left out. Our F1 score is then 0.97 for our cancer-free patients. So this was a really good score overall for the first class. Looking at the cancer patients though, we have 0 precision because we haven't predicted any cancer patients. That also means that our recall would be 0 and our F1 score would be 0. If we look at the accuracy though, we do see we have 95 as I mentioned previously. So if we only look at accuracy, the score is really, really good. But if we look at the other metrics, we can actually see that the result is really bad. The macro average kind of gives you the average of the two. And that's unweighted. So we do see that we have a score of 49, sorry. And you want to use macro average instead of weighted average because macro average actually doesn't care about how many samples is in one class. It's just going to take the average of the two classes. And that it basically accounts better for unbalanced data sets. That's what I'm trying to say. So in this case, we do have a macro average of 49 out of F1 score, 50 for recall, like because it's the mean of recall and precision, and 47 for precision here. So we do see that we have some I wouldn't say good, but it's like obviously this is really bad, right? These average scores could indicate that it's somewhat decent, but when you look at the class individually, then you see it's actually horrible. So let's take the example I mentioned where you predict 2 patients having cancer and they actually do have cancer. The way I did this is that I just said the first 98 patients are cancer-free and the last 2 have cancer. So now I know that they line up with the data set that I've created. So if we try and predict this, then we see that we have some different numbers now. Now we actually, for our cancer patients, do have some metrics that are not just 0, so we can actually look into what's going on here. As I mentioned, also, we would have a high precision and a high recall in the case of our cancer-free patients because we are predicting a lot of them, but we are still predicting some cancer patients in our cancer-free predictions. Therefore, our precision won't be 1, it will be a little bit lower. Our recall is 1 because we've predicted every cancer-free patient correct, and our F1 score for cancer-free is also really high. Now, if we look at the cancer patients though, we have a precision of 1, which means that it's very trustworthy when it predicts a cancer patient because every single prediction that was done on a cancer patient was correct. So we can definitely trust the prediction, but we've only predicted 2 out of 5, so our recall is going to be low, and we do see it here that it then represents for 40% or a score of 40. So our recall is low, but our precision is high. And if we look at the F1 score, we also do see that we get an F1 score, which is somewhere in between these two, which is the harmonic mean of those two scores. Again, accuracy says 97, so accuracy in this case would say that the model is even better and almost close to perfect, which is it's somewhat true, but not really, because again, accuracy doesn't tell you what's going on and why it's doing bad. You would never know the recall or how many of the cancer patients you have predicted out of the total cancer patients. Again, looking at the macro average, we do see that we have a 98 on precision, which is really good, because now like that would indicate our model is trustworthy, because we do predict our cancer-free patients very well, and when we predict cancer patients, we also do that very well. So this score is very representative of what's going on. A recall is 1 for our cancer-free patients and 0.40 for our cancer patients. So we get a macro average of 0.70. So this is definitely a number. Given our example, I would think that I could improve, and this is what I would want to optimize. I would want to get a high score for both of these. You'd never be able to get a perfect one, as I mentioned, but you'd be able to get a somewhat high number for this, and I definitely think in a real world case that I could achieve, given this problem, a higher recall. The reason for this is that I've made a baseline. So my baseline here is predicting everyone to be 0, and I do see the macro average to be 50 for our recall. So only going up to 70, I believe that there's still more that you can achieve using that. So using a baseline score, which I've done here, I've just predicted the most common class. This is what you want to beat when you make your model. If you can't even beat just predicting the most common class, then your model is not very good. Then lastly, if we look at the last prediction here, I've tried to create a scenario in which where your precision would be low, but your recall would be high. And this is going to be for our cancer patients. So I'm predicting the last 13 points in the data set to be cancer patients. So you see, I've just said the first 87 should be cancer-free, and the last 13 should have cancer. And when I make my classification report, again, we have somewhat similar number for our cancer-free patients. However, this is the first time that we do have a precision of 1 on our cancer-free patients. And this is because all of the 87 patients that we predicted as cancer-free also were cancer-free. So it's very, like that was 100% trustworthy when it makes its prediction. But we still are missing some of the cancer-free patients, hence why the recall is 92, so it's a bit lower. Now looking at the cancer patients, we can now see that the precision is 0.38. And that's because out of the 13 that we predicted of having cancer, only 5 of them actually had cancer. So now it's not very trustworthy when it says a patient has cancer. However, we have made sure that all of our prediction manage to contain cancer patients. So somewhere in our cancer predictions, there are cancer patients, but we don't know which. And this is also represented by the F1 score, which is then 56. So this is, in this case, we would try to optimize for precision, where in the last case, we would want to optimize for recall. Looking at the macro averages as well, we do see that both the precision is quite much lower than the last example, but we do have a way higher recall. So, and then you have the average, the F1 score as well as kind of a metric to give you a harmonic mean between the two. So the point for this was to kind of give an insight into the different kind of scenarios, and depending on your problem, you would want to optimize for one or the other metric. But it's important to try and look into what's going on behind the scenes and actually looking into the different metrics and not just use accuracy, or don't just use F1 score, but definitely go and look at the individual metrics, both as the average, but also on a class by class level, so you can see which classes are doing well. I'm going to be making another video on how you can counter a situation like this where you have underrepresented classes. It's something called data augmentation, and I think it's a whole topic for itself, so that's going to be for another video. All right, that's kind of the explanation and the introduction I have for the machine learning metrics and performance metrics for your models. Hopefully this was an insightful video for you to watch, and you learned a thing or two about the metrics and also the importance of it. As I mentioned earlier, I will be having videos about data augmentation, but I also have a video planned for bias in machine learning. A previous classmate of mine made her bachelor's thesis about bias, and it actually got released in a newspaper. So I think it's a very, very important topic to address, and also very interesting to look into. So definitely be looking forward to making that one. If you have any ideas for any videos, definitely leave them down in the description. Remember to hit the bell button and subscribe in the bottom as well. I really much appreciate it. This is very new for me, so I appreciate any feedback that you can give for me. So yeah, thank you for watching, and I'll see you next time.